Okay, so let's talk water, to continue talk about water. We have water number 2. Okay, very briefly we review the water. We talk about the water, the chemicals, total is 18. And we talk about the structure of the water, which is O. H is covalent bonds. Covalent bonds, and they connected with another molecule of water is with hydrogen bonds. Just say hydrogen bond, covalent bond, and we talk about the angle is 104.5 degree. We talk about the distance. This is 0.18 nanometer. 0.10 nanometer. This is 0.18 nanometer. And we also talk about the chemical structure. We call it sp3 hybridization, hybrids, and the hedro arrangement. This is, we spend a lot of time. We review about the basic chemistry, what is the sp3 hybridization means, coming from the Dr. Linus Pauling back in 1950s. Then we talk about what is a free water versus bound water. Then we talk about the soft water versus hard water. And we spend lots of time talk about moisture content versus water activity. And this is a very important concept, so we're going to still continue to talk about here. We would love to start to talk about moisture content and water activity, the relationship between that. So it's become, the topic is sorption isotope. Okay, so how they get it? We mentioned some at the end of the last class, but we're going to start from the beginning to say. So what is a sorption isotope? We draw a very typical figure. The x-axis we call ERH, equilibrium relative humidity. So that's 100%. And that is equals water activity multiplied by 100. And the y-axis, this is the moisture content. We also call it an equilibrium moisture content. And then we get the sorption curve, or we say sorption isotope curve looks like this. Goes this direction. And then we mentioned that based on the value of the water activity, we could cut these into different sections. So we do 0.25, 0.5, 0.75, and 1.0. Then we can basically, or we can manually cut the products into 3 different categories. In the first category, these are, we call it a mono layer. Second one, we call it additional layer. And the last one, we call it a capillary water. And the mono layer, most of these are bound water. And the capillary water, most of these are free water. We also call these coming from condensation. So this is a sorption. And we also mentioned about different food products. Okay, we give the food products. Like this is the first category is chips. This is a fruit, a roll up, or chewy chocolate balls. The last is fresh produce, or we say meat products. And then we talk about shelf life, texture, and the color under the moisture content, the briefly. So this is what happened. How they get this curve? This is back in like 1930s. The people doing the chemistry, doing some of the research, try to see the sorption, desorption. We call it adsorption and desorption curve. And how they do it, they did most of the time is on cornstarch. So, you know what is cornstarch? That is a corn used to make as maize, the corn maize. So there's a joke always we have is that when the first time when we go to see the corn maize, we think those corn can eat. So we just steal some of them, put in the bags, and we go home, we cook it, we never can eat it. Because those are not sweet corn, those are the corn starch. It's used for further manufacturing, become a starch, become like a sugar. But the people doing the corn starch to see the absorption and the desorption use that as a material. So how they do? They did that in a closed chamber. And they put a pan there. And then they put a holder. And then they put a product. Let's say you put a corn there, okay, starch corn there. And then in here you put some of the water. And then you, of course, you're going to add like salt, sodium chloride, calcium chloride, all different components. So you add the food products. If it is dry products, they will be absorbed, the solution. If it is a moisty products, there will be desorption. So if you can draw, we can draw like a, here is, the products will be absorb or get water, lose water. And after a certain period of time, they will reach equilibrium status. That's why we call these EMC, equilibrium moisture content. It's a balanced status. So people get this sorption curve. Now, what's a desorption curve looks like? It's surprising. Goes here. It's a desorption curve. So we say desorption, and this one is adsorption. Okay, then this gives you some question. What is the question thing we're going to have to talk? First of all, this figure morphology, we call it sigmoid. And the sorption is not reversible. And we call it is hysteresis. So from the food safety, food microbiology safety standpoint, we don't want this to happen. So think about, if there is a food product, you can absorb moisture when you want to use it. And if you don't want it, you just take out all the water. Then the bacteria will never grow because there is no available water there. And the water activity is absolutely close to zero. So the food safety will never, food microbiology safety will never be a problem. But that's not going to happen because the desorption is not reversible. Now, why it's not reversible? This comes out with a great food chemist. He's Dr. Ted Labuza. he did lots of the literature review back in 1950s to 1960s, and gave some of the hypotheses and some of the conclusions. Dr. Ted Labuza, his last couple of students got a PhD degree of food science, specializing in food chemistry from MIT. So after 1967, the MIT no longer has a PhD program. I know another faculty there, and Dr. J has he was Dr. J's, his last name is Antonio, and he was Dr. J's PhD committee back in 1990s at Oregon State University. So Dr. Ted Labuza is one of those last batch of students who graduated PhD of food chemistry and food science from MIT. Later on, he worked at University of Minnesota at Twin City for 30 or 40 years. And he passed away in 2023 December. Okay, I met him a couple of times at IFT meeting. I just briefly talked about that, but because I don't do research for chemistry, but when you read the manuscript or read the book, he did a lot of the contribution in this area back when he was students and the early career of the faculty. So what is that? He thinks this assumption, the major difference coming from the capillary water. And he thinks the capillary water section is like an ink bottle. So this comes out with his best, not the best, his theory is ink bottle model theory. I think this is the most easily understand and the most well understand model to talk about absorption and desorption. There are lots of theory about that. He thinks the capillary water, what it looks like an ink bottle. I don't know whether you still know ink bottle. I used it when I was students a long time ago. When I was in China a long time ago, started writing. So we used ink bottle. You have a pen, go there. So he thinks the capillary section looks like an ink bottle. There is a neck and the bottom. So therefore, there is a two radius, a big capital R and a small r. Here you have a big capital R and a small r. So when you do the absorption, which means the water is coming, okay, when the water is coming, it depends on how thick the big R looks like. So this is absorption. Depends on how large the R. Because when you feed it more and more, the speed or the time depends on the big R. Now once you do a desorption, he thinks, let's say this is not filled with all the water. Okay, I'm gonna have to take them out. It's rely on the small R. So depends on the small R. That's why you have this hysteresis, the sigmoid figure comes out. And I think it's best to understand. So let's think a little bit more about here. What does the capillary section looks like? Why he comes out with this? The textbook didn't mention directly, but I can tell you the background. So what is the background? We need to talk about the capillary force a little bit. So this is a little bit of physics, and I said that this class has a little bit of physics. Okay. This is a capillary tube, let's say. A very basic science, a basic physics. What's the water going to be looks like? The water will be in an angle is is this way. The mercury is opposite. Okay, so when you have this, and the water is even absorbed a little bit on here, so they generate a force. The force kind of like goes this way, and it goes that way. That's called capillary force. And then you know in the physics, this is we'll have a G, and that's a F, that's a F. So you can do a angle. So that gives you, this is alpha. So you have like 2F, that's cosine, alpha equals G. You keep the balance. And then this is out, and this another force is going inside. So F sine alpha equals like F, another F. Okay, that's a capillary force. So the theory here is he thinks lots of the food products, let's say a meat or fresh produce, is composed by, you can think about, is composed by a lot of these capillary section, like composed by lots of looks like capillary tubes. And we know there is another formula, which is log E water activity equals -2 sigma R V and R T. So what this means, which means the water activity and the radius, this R is the radius of capillary water is correlated. And you can think about this whole thing is fixed number, is A, okay? So what all these things means? The theta, that's a surface tension. And the V is the absorbed volume. And this R is heat constant. And this T is Kelvin. And we need to know that is degrees Celsius at 273. But we can say that's a fixed number of A. So that means water activity and R, there is a relationship. The radius of capillary water has a relation. So they did the research back in the 1950s. If the radius of capillary water is only is only 1 nanometer, the water activity is 0.373. That's very dry. If it's 10 nanometer, this all of a sudden jumps to 898. If it's 100 nanometer, this becomes 0.989. If it's 1,000 nanometer, which means 1 micrometer. This is typically, we think what the meat, the capillary water section, the radius looks like. Then the water activity close to 1.00. This is very easy to understand. And he also think about, there is another relationship is the pressure. The pressure used to, the pressure products, and will cause the water drip. That is water drip, that is opposite direction. If the 1 micrometer, the radius is large, the water drip, needed pressure is very low, is only 0.0148. If it's if it's 10 micrometers right here, you need 0.148. And if the last one, you need 14.8. So that's a way to understand why the meat is easier to be dripping. Because you just press a little bit, the water comes out. They think the theory is that the majority of them are filled up with capillary water, and the capillary water relate to the capillary force. And he thinks the capillary water is not a straight tube. The morphology looks like ink bottle. That's why absorption and desorption, it is non-reversible, and it is a sigmoid morphology. Okay, so that's something very interesting way to mention. Now, we want to say that why this is important. Why these curves are important? Because we can decide it. We can use the estimation there are a correlation between the water activity and the equilibrium moisture content, and to see how sensitive they are to the environmental moisture change. So you may get some curve like this. This is, we call it a high growth copic. So yes, high growth copic products. That is very typical for coffee bean powder. They are very sensitive to the environment. You may get a curve like that, like this. I didn't draw very well. That's not very sensitive to environmental moisture. And you also could get a curve like this. This is a typical of products with high salt and high sugar. Now, why this is important? Because all of things, it depends what types of packaging we should do. That's why in the old time, when they developed those things, they have all these theory about it, all these morphology about it. Now, we wanted to say, based on this, okay, we mentioned about these. In the history, people developed a different mathematical model to see the absorption isotherm. We want to introduce you several. We'll talk about the equation. We want to introduce you some. And the summary is also did by Dr. Ted Labuza back in 1950s, and it's well published and described in all kinds of the textbook, including the book we're using. So, the first model, we call it a Langmuir equation. This is lots of little bit math there. Okay, what is a Langmuir equation? It's AV equals KBVM plus AVM. Okay, what is this one means? V volume absorptive. A, that's water activity. What is K? 1 divided by P. This is partial vapor pressure. What is B? This is just a constant. What's the important thing? VM is important. That's a monolayer volume, or we say value. for here, this section, okay? Now, why this equation is important when they generate it? This is in 9012 or 9010s just. Because you could write a figure to describe it. So the figure looks like x-axis is A, y-axis is AV. This is a primary function, I can only say that. You will get this section is, this section is Vm. That will be called the intercept. Okay. Yeah. Oh, sorry. This section is KBVM. That is called intercept. And we also can get a slope. A slope is equals Vm. So once you have this figure, you will get to know what's Vm looks like. Okay, by the way, okay, this one, y equals ax at b. A little bit of math. So when you draw a curve, looks like here. This is x, this is y. So you go here. What is slope? Is a. What is intercept? Is b. Okay, so the b called the intercept, and the a is called slope. Okay, so that's a Langmuir equation. At the beginning, people use this. But Dr. Labuza pointed out that Langmuir equation is originated from air, from solid, and it's assuming water absorption is section by section. This whole thing is not fit for most food products. You can understand, this is like we do a thermal inactivation study of bacteria. We talk about a linear model. It's not works all the time, but we still have it. Because it's not. We assuming the water absorption section by section. Certainly it's not. You have a tomato there, you not absorb within section by section. So, the scientific area, in 1938, there's three scientists developed a new equation called the BET equation. The BET equation, named by Brunner, Emmett, and Taylor in 1938. So what it looks like, the equation a little bit complicated. Is A water activity by V, that equals CVM add AC minus 1 and CVM. So what is A? That's water activity. What is V? Absorbed area. What is C? That's a constant of heat absorption. And Vm, that is always important, the monolayer volume, or we say value. So then we get another curve. What's a curve looks like? We get another curve. X-axis is still A, y-axis this time becomes A divided by 1 minus A and V, and then you have another curve comes out. What's going to be the intersection looks like? That's intercept equals 1 divided by CVM, and the slope equals C minus 1 CVM. That's a curve looks like that. And why this is important? Because we get a VM value is more accuracy compared to the Langmuir equation. So what we can get is S water absorbed have an equation. And I want to tell you our textbook have a big mistake, but it's a small typing error. Okay, what is that? That is equals VM monolayer value. You come out from here, okay? Multiple by 1 divided by the m molecular weight of water, multiple by Avogadro constant, and multiple water area or water absorbed area. So VM we don't know. VM has to come out from here, okay? But the others we know. This is 18, that is 6 multiplied by 10 to the power of 23, and the last one is 1.06 multiplied by 10 to 20 cm squared. That's our textbook. Right, it is wrong. It's minus. If 1.6 10 to the power of 20, that will be more than the whole Earth. Okay, that's why I told you there's some mistake of the textbook. So when you do the calculation, you could get the value is approximately 3.5 VM. 3.5 VM so multiplied by 10 to the power of 3. So we will know the area, how large the area is, what is absorbed. Once we get a VM value from here. So then people are doing some of the research. So they do a different analysis of the food products. They find that the BET equation is better for, it's very variable, it's better for dry products. So let's say dry apple, dry potato. In other words, this is better for our products with a water activity about 0.1 to 0.5. Because it could be very accuracy to calculate the monolayer value. So basically it's right here. But how the product is in the other side, which means the product has a more correlation between water activity and equilibrium moisture content. Therefore, later on, in 1981, they have another equation comes out called the GAB equation. The GAB equation named by 3 persons, which is Guggenheim, Anderson, and De Boer. So Guggenheim, this is Anderson, then the last one is De Boer. So what it looks like? This is directly go to equilibrium moisture content. That equals W K A W 1 minus K A W multiplied by 1 minus K A W and C K A W. So we just go briefly. Here, W, K, C, these are constant. Once they have this GAB equation, this is going to cover the food products. Covered the water activity 0.1 to 0.9. And later on, about like 5 to 10 years later, people say, this is not going to cover everything. For example, like a meat. You may not be using this to explain. Therefore, it comes out with a modified GAB equation. I had to publish the paper, talk about that, but I don't think you're going to read it because it's all mess. So this will cover the left 0.9 to 0.999 range of the products. So same as our bacterial growth model or inactivation model. For the absorption, for the chemistry area, they have those software included all these equations, and then you added, you can see the Langmuir value, BET equation value, and also the GAB equation value. Because the idea is we want to see the desorption, the mass, then determine how sensitive the products to the environmental moisture, to see the correlation between equilibrium moisture content and the water activity, then decided what type of the packaging they should use. Regarding this, we'll talk about the slides. We'll use the slides next week, Tuesday, when we finish the last part of the water. There are several things I want to explain to you. There are one mistake in the book. You have this book in the eCampus. So there is a mistake here, which is at page, I believe in page 20. It should be somewhere the calculation. It's at page 21 to 22, especially page 22. The area of water molecules, that should be I pointed out, that should be the 10 to the power of minus 20, not 10 to the power of 20. And also you can see they didn't do a good job of proofreading. This whole section is repeated twice. Okay, so that means it's difficult, so they didn't understand. Okay, one more thing I want to ask is that.
They messed that up in the first 20 pages.
Yes, lots of mistakes. I want to explain this figure. This is also a tricky one. So what does this one mean? They have this figure looks like here. This is also a mistake, and I asked the people doing the research for chemistry to explain to me. Okay, they do a delta T, and this is so-called LMP P0. Okay, then they get a curve. When I teach for the first 3 years, I don't understand this one very well. Then they get a curve. It looks like this. Okay, they get a curve like that. They get a curve like this. They are using cornstarch to see the impacts of the temperature of the water activity. So they get a curve M1, M2, and M3. Okay, now there is one sentence. They said the higher the temperature, the lower the position. Now, where did they get this come from? This comes from Clausius and Clapeyron equation. We mentioned very briefly. This is an easy one, to be honest with you, which means temperature increase, partial vapor pressure increase. That means water activity relatively saying is increased. It's just that simple. Now the reason is the Clausius-Clapeyron equation originally is non-linear. And people want to make it understandable. They think the linear equation is understandable. They make it become linear. Therefore, it comes out with P0 equals negative delta H is R, and then they have this so-called T2 minus T1. And then you put the negative there. And lots of the textbook even write this one as like delta Q. That makes it more complicated. What happened is, this conclusion is right. So, but it's not easy to understand at the beginning. Okay, if the higher the temperature, what this means, if this is a large, if you have a reciprocal number of T, 1 divided by T, that means the T is smaller. That means the lower the temperature, the higher the position. It's not the higher the temperature, the lower the position. But what they're missing, this is T2 minus T1. So this should be delta T. Then you understand. So give you an example. If T1 equals 10, T2 equals 30, what you have here, that is 30 minus 10, the denomination is 10. Then you don't forget there's a negative here. So you have to get the absolute value. And then you go here, let's give an example. Second one, T1 equals 10, T2 equals 40. Then you have absolute value is 40 minus, no, obviously this is higher. This is larger than number. That's what it comes from. This should be the delta T. So once you messed it up with that T value, that sentence becomes very confusing. So that's why I just explained to you. The figure is correct, but this sentence, the sentence is correct, but the figure is confusing because it's delta T is not the T. And most of the time, they think, I just gave you the number, they think this is very small. This is about like 0.001 or 0.01-ish. So that's, they want to tell you the conclusion is the higher the temperature, the higher water activity will get is in the food products. So that's the classic Kelpian reaction they mentioned, and this is what they talk about in the figure 1.19. But the description is confusing. Okay, so that's what we talk about. Okay, so this section we talk about is these equations, and I'll just simply move the camera to the other side. Then we are gonna, on the other side, we're gonna talk about the ice. So that's easy. So we're gonna go to talk about ice. We have roughly about 20 minutes. We're gonna talk about the ice. We'll just move to here, then we can talk about the ice. Oh.